Yeah. If I could choose, I would be somebody. Thank you. Oops. Thank you very much. Yeah, today we'll talk about just the semiconducting materials, but then we'll start building devices out of them, and one of them will be the diode. The other one will be the transistor. All right. Welcome back, everyone. I hope you had a good break. So, if I'm right, we've got 3 weeks of classes left. And so what we want to achieve in those 3 weeks are the following. We're going to start today by talking about semiconductor materials. Once we've done that, we'll be able to use these materials to make semiconductor devices. The devices that we want to make are the diode, which we've already talked about. And we kind of designed the rectifier circuit, the AC to DC converter out of the diode. The other device that we'll want to make is the transistor. And we're going to use that transistor as the building block for the logic gates that we've talked about, before the break came around. So then once we've done that, we'll talk a little bit about some other applications of digital circuits. And in parallel with doing all of that, we will prepare ourselves for the final project, which we're going to start this week. So probably the way it will work out is Wednesdays will probably be focused on getting ready for the lab activities. And then the Mondays are going to be like the semiconductor stuff and building diodes and transistors and stuff like that. Okay, so let's get started. We're going to start with today is probably a pretty qualitative kind of trying to get a bit of an understanding for semiconductors and why they're special materials. So most semiconductor materials are silicon. So we're going to focus on silicon, but it's not the only semiconductor material. Germanium is another common one. We will focus on silicon because a lot of the chips and things that we use in the lab to build our circuits are all based off of these silicon devices. Silicon is the 14th element in the periodic table. So silicon is 14th element in the periodic table. So that means it has 14 electrons. It also means it has 14 protons in the nucleus. So what we're going to care about mostly the electronic structure of the silicon atom. So I'm going to draw kind of a cartoon of the silicon atom. So here is the nucleus. So the nucleus has 14 protons and 14 neutrons. And so that means it has a charge of plus 14 for just the nucleus. Of course, the entire atom itself is neutral. And so that means there's going to be 14 electrons around this nucleus. I don't know if Physics 200, is that a course that is next term? Yeah, okay. So I don't know, have you talked about the like electron configuration in any like a chemistry class or something like that? Or you've seen it somewhere maybe? So I'm gonna just tell you the electron configuration of silicon. So the electrons are organized in different shells, and the different shells can also have different orbitals. So the innermost shell is called the 1s shell, and it can occupy, or it can be filled with 2 electrons. So this 1 is going to represent the shell number. The S is not going to really matter for us, but it's called the orbital. That's something you'll talk about more if you continue and take some 3rd and 4th year quantum mechanics and things like that. And then the 2 is going to tell us how many electrons can go in that orbital. So the number of electrons in the orbital. Okay, so the first one, 1s2. So I'm going to draw kind of a cartoon atom here. And so we'll say this is that first shell, this is the 1s shell, and I can put 2 electrons in it. And so there it is. We need to place 12 more. The next electrons are going to go in the second shell. So it's shell number 2. Shell number 2 has an s orbital that can take 2 electrons, but then there's also a so-called p orbital. So it's the second shell, p orbital, and I can put 6 electrons in there. And so this will be a total of 10 electrons once we place those. And so here's my second shell. And I want to place 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. All right. We still have 4 more electrons that we have to put in our atom, and they're going to go in the 3rd shell. So there is an 3s2 orbital, so I could put 2 electrons there. And then there's a 3p. It can take 6 electrons, but I've already used up 12 of my 14. So all I can do is I can put the last 2 inside this p orbital. So I'll draw a 3rd shell. And we'll put in 4 electrons. Okay, so that's the basic structure of the silicon atom. And what's going to be important for us is that we have not filled this last orbital. It can take 6 electrons. We've only placed 2. And so that's going to be important. So there is room for 4 more electrons in the 3p orbital. So it can take 6, but we've only placed 2. All right. The other bit of terminology that we're going to use is that the outermost shell is going to be called the valence shell. And then all of the electrons that are in these inner shells are going to be called core electrons. So we'll call this the valence shell. and the electrons and the inner shells are called core electrons. And it will turn out that for us, all the important action that we're going to care about is going to have to do with these valence electrons and this outermost shell. And the reason is that the core electrons are relatively tightly bound to the nucleus, whereas there's a little more freedom in what can happen with these valence electrons. Okay. So our outer or valence shell is only partially filled. Okay, so that's just a single silicon atom. What we're going to be interested in is like a solid chunk of silicon. And so we're going to talk about the bonding of the atoms that make up the solid. So we're going to attempt to draw a 2D representation of a piece of solid silicon. Now, of course, solid silicon is a three-dimensional object. It's not a two-dimensional sheet, but it's going to turn out that what we draw for this 2D representation contains all of the essential physics that we're going to need. And I will show you a more realistic picture of a three-dimensional piece of silicon once we've drawn some of these pictures. So what I'm going to do is I'm going to draw a bunch of silicon nuclei, but this time these little black circles don't represent just the protons and neutrons of the nucleus. They're going to represent the protons and neutrons of the nucleus plus the core electrons that are in the inner shells. So I'll draw a 3x3 chunk of silicon, like so. And let me just put over here, like our little legend, that this represents the silicon nucleus plus the 10 core electrons. And so that means that this object has a charge of plus 14 from the nucleus and minus 10 from the core electrons. So overall, its charge is plus 4. I mean, I guess technically the charge is 4 times the elementary charge, but let's just call it plus 4. All right. So what I need to draw now are the valence electrons. And each of our silicon atoms has 4 valence electrons. And so I'm going to draw 4 valence electrons for each of them. I think that's all of them. Okay. So what happens is, notice that if I look at this piece of silicon, the silicon atom right in the middle, it has 4 nearest neighbors. There's other neighbors that are further away, but we're going to focus on the 4 neighbors that are closest by. And I mean, I've drawn only a 3x3 section, but if, this would be a huge piece of solid with Avogadro's number of atoms. And so any one of these atoms is going to have 4 closest neighbors. So each silicon atom in the solid has 4 nearest neighbors. Now, what we said is that our valence shell was only partially filled. It's partially filled with 4 electrons. It has room for 4 more. And so what happens is that neighboring silicon atoms end up sharing some of their valence electrons. And that's called a covalent bond. And so we're going to share these electrons with our neighbors. And thereby, in some sense, we effectively fill this valence shell. So these are all the covalent bonds. And I haven't drawn, if I drew more silicon atoms, these electrons on the edges would be shared with, other atoms that we haven't drawn. Okay. Good. So these are strong covalent bonds. Covalent is kind of a reasonable term for this bond because co kind of means sharing and valence is referring to those valence electrons. And so we're sharing our valence electrons to form these bonds. Okay. So if we accept that picture, at least qualitatively, then what we would say is all the core electrons are bound to the nucleus, so they can't conduct electricity. All of the valence electrons are participating in these covalent bonds, and so they can't conduct electricity. They're bound up in these bonds. And so there's no free charge in this material that's able to conduct electricity. And so this pure silicon is a poor conductor. So most valence electrons in pure silicon are participating in covalent bonds. And so there's no mobile or free charge available to conduct electricity. Now, if we were able to say break one of these bonds, that might free up some charge and it might allow for some conduction of electricity. And so there's going to be some kind of characteristic energy that you would have to provide in order to break one of these bonds. How could you inject energy into your material? What could you do? What kind of energy sources are, like, what's a common one? Yeah, well, electricity, we're trying to produce the ability to conduct electricity. So we're going to have to put in some kind of other energy to free up these charges. Heat. Yep, that's a good one. So we can create mobile charges by heating silicon. So the energy, it doesn't matter what we call it. I'm going to call it delta. So the energy delta required to break a covalent bond is, so delta is something like an electron volt. If you convert that to joules, it's like 1.8 times 10 to the minus 19 joules. I think it's most instructive to convert this to temperature units. So kBT, Boltzmann's constant, times temperature is in energy. And so that means delta divided by kB has units of temperature. And this turns out to be something like 12 or 13,000 Kelvin. So that's That's quite a high temperature. So that means if you have a chunk of silicon just sitting on the desk at room temperature, 300 Kelvin, the thermal energy in your material is way less than delta. And so that means it's very unlikely that you're going to break many of these bonds. And so all the electrons are still in these covalent bonds, and you don't have a good conductor. Okay. So since delta over KB is much less than, I don't know, let's say T room, which is around 300 Kelvin, silicon is not a good conductor at room temperature. All right, so what we're going to do is it's not as if there'd be none of these covalent bonds breaking. You have this collection of a huge number of covalent bonds, and there's some probability that's based off of the temperature of the sample that you're going to break some of them. The probability of that bond breaking is very low, but if you have a huge number of those bonds, because of you have Avogadro's number of atoms in there, some of them will break. So what happens when that happens, when we get a broken bond? All right, so let's see, at room temperature, very few covalent bonds break, but it's more than zero. So let's see what happens when we do have a broken one. So I'm going to repeat the picture that we drew. Here's my nucleus with the 10 core electrons. I'll draw 9 of them again. And we'll place our valence electrons, 4 for each atom. And then I'm going to draw my covalent bonds, but we'll draw one of them as if it's broken. Okay, so we'll do these bonds on the edges. Okay, so and then we have these interior covalent bonds, and one of them I'll assume has broken due to the thermal energy. Okay, so there's this one which will maybe indicate this as a broken covalent bond. All right. Well, if these are not participating in a bond anymore, then this electron is far away from the nucleus, relatively speaking, and so it's only weakly bound to its host atom, and it's because it has some thermal energy, it can detach and it can move throughout the sample, throughout the material. And so it's able to conduct electricity. And so what we could do is we can take this one electron and it moves about the material. If we apply a voltage across it, there'll be an electric field inside the material, and there'll be a force on this, and it moves in the direction determined by that voltage difference, and it creates a current. Okay, so each broken bond creates mobile electrons. But it does something else as well. If one of these electrons takes off and has moved somewhere else in the sample, like maybe it's off the screen somewhere, now we have essentially a vacancy of an electron. And we're going to call that electron vacancy a hole. So this is an electron vacancy, or a hole. Now what happens with this hole is I could have an electron here jump in and fill that hole, but then I have a hole over here. And now I can take, I don't know, this electron and it fills that hole, and now my hole's over here. And so effectively, instead of thinking of different electrons always filling that hole, we can imagine this hole is moving throughout the material as well. And so we take an electron and it jumps into that hole, and so now our hole's over here. And then this electron jumps into that hole, and so now our hole's over here. So we can have both the free electron moving throughout the sample and this so-called hole moving about through the sample. But if I keep having electrons hop in this direction, that's the same thing as having an effectively positive charge move in the opposite direction. And so it's another mechanism by which you can conduct electricity or establish a current. Okay, so each broken bond creates mobile electrons and mobile holes. The mobile electrons and holes can conduct electricity or equivalently establish current. The problem is that right now we have so few of these mobile electrons and holes that the conduction is pretty poor. All right, so before we move on and try to manipulate the properties of our silicon, what I want to do is I want to show you that this 2D picture is reasonable. So this is exactly what we've drawn down. It's just a nicer version of my picture. This is the silicon atom, and here's our 2D representation of a solid piece of silicon with all these covalent bonds. So what I want to take away from this picture is that here's the realistic kind of view of a solid piece of silicon, so the crystal structure of silicon. And you can see it's quite complicated. But they've highlighted part of this. And if you focus on this silicon atom right here, these lines are going towards its nearest neighbors. And so this is a 3D picture. The important point is that each silicon atom has 1, 2, 3, 4 nearest neighbors, and these lines represent those covalent bonds. And I could pick any one of them, and I could find 1, 2, 3, 4 nearest neighbors with 4 covalent bonds. And if you break any one of these bonds, you get a mobile electron and a mobile hole. Okay, so there's the more realistic picture of what a silicon atom looks like, but we'll stick with this 2D representation because it's easier to draw and visualize. All right. So if that was the end of the story, it wouldn't be that interesting. We would just basically conclude that these materials aren't good conductors. So it's not the end of the story. We can manipulate the let's say, electronic properties of silicon via doping. And so we're going to dope these things. What does doping mean? What we're going to do is we're going to take an occasional silicon atom, and we're going to try to replace it with something else. We're going to replace it with a dopant atom that has 3 or 4 valence electrons. Sorry, 3 or 5 instead of 4. And let's see what happens if we do that. So we'll try to replace an occasional silicon atom with something that has either 5 or 3 valence electrons. We'll start with 5. So when we use something with 5 valence electrons, that's called N-type doping. It's called N-type because we're going to add an extra electron to our structure. And so that's like adding a negative charge carrier. So N is like negative charge. So we're going to use dopant atoms with 5 valence electrons. Okay, so in a practical sense, we can use phosphorus. It's I think it's element number 15. So it's right next to silicon in the periodic table. So if silicon has 14 electrons, phosphorus has 15, 5 in the valence shell. Dopant, which has 5 valence electrons. So specifically, the electron configuration of phosphorus is 1s2, 2s2, 2p6. Those are going to be the 10 core electrons identical to silicon. And then 3s2 is filled. And then there's 3p. But instead of 2, we're going to have 3 electrons in there. And so that's the key difference, is that extra electron in the valence shell. So the way you could do this is, you could start with like a silicon powder. Maybe you're grinding your powder up or something like that. And then you take a little bit of phosphorus and you sprinkle some in there and you kind of mix it evenly. Then you take that powder and then you grow your bulk material, however, whatever that process is. And so you can control how much phosphorus you sprinkle in there, and you can vary the concentration of these dopants. So the doping concentration typically can vary from 1 part, or let's say 1 dopant per 1,000 silicon to 1 dopant per 1 billion silicon atoms. So this ratio 1 to 1,000 would be like a heavily doped material, and 1 per 1 billion would be lightly doped. And so, that's 6 orders of magnitude difference in concentration, and you can imagine that that's going to have a large effect on the electronic properties of the material. So we're going to try to draw our doped silicon. So I'm going to start with these black ones are going to be our silicon nuclei with core electrons. I'll draw 8 of them this time. I'm gonna leave the one out in the center. So here's our legend. Silicon nucleus plus 10 core electrons. Its charge, like before, is +4. All right, and so here's our dopant. There's our phosphorus. This is the phosphorus nucleus plus 10 core electrons. Being element number 15, the nucleus has 15 protons in it. And so the nucleus is charged +15. The core electrons are -10. And so the net result is +5. So that's going to be important when we start talking about like our diodes and semiconductors, is that the dopant, not only does it introduce an electron, an extra electron, it also introduces an extra stationary charge into what people would call the lattice of the crystal that we're trying to construct. Okay, so let's put in these electrons. So we'll start by putting, let's say, 4 around all of our silicon atoms. So we keep drawing similar types of pictures here. Now I've got my phosphorus, so it has 4 valence electrons, but then it's got this other one, this extra one. All right. The same thing happens. We still have covalent bonding, and so we can draw all those covalent bonds again. Here we go. And you can probably imagine what's going to happen is we're going to make all these covalent bonds with our nearest neighbors. But then once we're done, we're still going to have an electron left over. And so maybe I'll draw this like, it's kind of hanging on to this nucleus, but very weakly. So weakly, in fact, that it easily detaches from its host nucleus at room temperature and is able to move throughout the material. And so it comes off and it can move throughout the material. It can contribute to current, conduct electricity, things like that. And so you could imagine, like I've drawn 1 dopant, but if we had 1 for every 1,000 silicon atoms, now all of a sudden we have a whole bunch of free electrons that are able to move around through our material and conduct electricity. So the extra valence electron in the dopant is not participating in a covalent bond. It is only weakly attached to its host atom. It easily detaches and moves throughout the material. Okay, good. We'll draw this picture again, but this time our dopant is going to have only 3 valence electrons. Now you may already be anticipating what's going to happen. Instead of introducing an extra electron, we're going to introduce an electron vacancy or hole. And the concentration of dopants will determine the concentration of these holes that we introduce that are, again, going to be able to freely move throughout the material. So P-type doping, or if we like, hole doping. In fact, maybe we should go back and we should call this N-type doping is the same thing as electron doping. Okay, so we're going to use a dopant with 3 valence electrons. An example is boron, B. Its electron configuration is 1s2, 2s2, 2p1. It's this time, the valence electrons happen to be in the second shell. So second shell is the valence shell. Does anyone know, we said silicon was the 14th element. Does anyone know what the 13th is? It's aluminum. And so you can dope silicon with aluminum. So it would have the exact same electron configuration as silicon minus 1 valence electron. I don't know too much about it, but there's some technical reasons why boron is a better dopant. Has something to do with how it diffuses into the material. So it's just a technicality. The important point for us is that we have 3 valence electrons. Okay, so we'll draw the same picture again. So I'll draw 8 silicon nuclei with 10 core electrons. And then I'll draw a boron dopant that's going to have 3 valence electrons. So silicon nucleus plus 10 core electrons. As always, charge is plus 4. So boron nucleus plus, so let's see, it's going to be just 2 core electrons. Boron is the 3rd element. Sorry, no, it's not. It is the 5th, right? So it's 1, 2, 3, 4, 5. It's the 5th element. So it has 5 protons surrounded by 2 core electrons. So the charge is going to be plus 3. Just thinking ahead, when we do start talking about like making diodes and stuff like that, I'm not really going to care that the charge is plus 3. What I'm going to care about is that the charge is 1 less than the neighboring silicon atoms. Okay, in any case, we'll draw all of our electrons. Most of them are going to be in covalent. Well, in fact, this time they'll all be in covalent bonds. The issue is going to be, however, that our dopant is missing a valence electron relative to the silicon. Okay, and so here's our covalent bonds. Okay, and now there is a missing bond. Missing covalent bond. And this is going to be our hole. And we get one of these holes for every boron dopant that we introduce. Now it's the same picture as before. Really what's happening is an electron from a different bond could fill this in, form a covalent bond here, but now we have a hole in this position. And then this electron jumps in here, hole moves here, and so on. We're going to imagine, instead of a bunch of different electrons always filling this hole, we'll just imagine the hole hopping around and moving throughout the material.
The movement of the covalent bond not affect the breaking up, I guess. Right?
Sorry, what's that?
The covalent bonds move, it's not the same as the breaking.
Yeah, I guess not. I'm not gonna lie. I don't know all the technical details of that, but that's the picture. Yeah, yeah. Okay, so we have 5 minutes left. Okay, so what we'll do is we'll introduce a little bit more terminology and then we'll wrap up for today. So doping is used to introduce what are called majority charge carriers. So so if there's majority charge carriers, that must mean there's another type. And so think back to the beginning when we were talking about pure silicon, we said we could add heat or thermal energy to break a covalent bond. So that still happens even in the doped material. And so occasionally, one of these covalent bonds will break and you will get holes and electrons that are able to conduct. Those ones are called minority charge carriers. The reason they're called minority is because they're very rare compared to, the number of charge carriers you get through the doping process, but they still exist. So when a covalent bond is broken, say due to thermal energy, the free electron and hole that are created are called minority charge carriers. All right. So we have these two types of doping, and what we want to do is we want to start making devices. Modern semiconductor devices are made by having sharp junctions between N-type doped silicon materials and P-type doped silicon materials. Or not necessarily just silicon, but N and P-type doped semiconductors. So modern semiconductor devices, and the ones that we're going to be interested in are going to be diodes and transistors, are made by joining N and P-type doped semiconductors with a sharp junction. We have 3 minutes, so maybe what we'll do is we'll kind of sketch out the diode and we'll see some of the picture, and then we'll analyze it maybe sometime next time or Monday of next week. So the diode has a single, it's called a PN junction. So this will be a junction between a P-type and an N-type material. So let's try to draw a chunk of semiconductor, and this will be our junction. So on one side, we'll have our, let's say, p-type material. And on the other side, we'll have our n-type. Okay, well, what do we know about p-type? Well, it's right here. We said that the dopants are going to have a charge of 1 less than the silicon. So I'm going to represent that as a bunch of minus signs. And so there's these negative signs, like so. And these are fixed dopants of the p-type. So these are fixed negative ions. Really, they have a charge of +3, but they're negative with respect to the silicon. I'm not drawing them, but there's like, for every one of these negatives, there's going to be like 1,000 to 1 billion silicon atoms that I'm not drawing. On the other side, I'm going to have the n-type. What color did I use for my n-type? I used red. And so there's going to have these fixed positive ions. Really, they're charged +5, but I'm going to draw them as if they're +1 because they're 1 above all of the silicon atoms. So this is plus is going to be fixed positive ions. Okay. Well, what else do we have? On the p-type side, for every dopant, we get 1 mobile hole. I'm going to draw my mobile holes as these little pluses. And they have these arrows, they can kind of swim around throughout this material. Okay, so these are mobile holes. And then on this side, we have mobile electrons. This device is going to be our diode. And in the last 30 seconds, let me just tell you what we'll talk about next time we pick this up. At this junction, I've intentionally not drawn the mobile charges inside the right close to this junction, because if you have a hole and an electron come together, they can cancel each other out. That the electron fills the hole. And so in this region, you end up with this, they call this the depletion region, because the mobile electrons and holes recombine. But if they do that, I've got these fixed charges here. I have positive charge on one side and negative charge on the other side. It's a bit like a capacitor, separation of charge, and they're parallel to one another. Electric fields point from positive to negative, and so you get this electric field that points in this region. If this has a certain distance, L, E times L tells you what the voltage difference across this region is. And if an electron drifts over here, the force on the electron is minus E times the charge. Well, E times the charge, and the charge is negative, so it gets pushed back. If this hole comes over here, it gets pushed back into this region because the electric field forces that positive charge back. And if you want to cross this junction, you have to have enough energy to overcome that potential barrier. That potential barrier is the threshold voltage that we talked about when we were talking about diodes, 0.6, 0.7 volts, something like that. Okay, so that's sort of the essence of the diode. We'll talk about it in more detail when we pick this up next time. Thank you very much.